everyone, welcome to this manufacturing systems technology part 2 module 15. We were discussing about control charts and we would like to see a little more of variable control charts. So if the quality characteristic as I think I had discussed earlier is measured or is a measurable quantity, you can express this measurable quantity further as a continuous variable, then it can be conveniently characterized by measures of the central tendency and variability related to the distribution that we are talking about, and so therefore that can be useful for controlling or for plotting the variable control charts. So typically these charts can explain the process data in terms of both location, in terms of the average, whether it is placed around the mean or it is significantly deviated from the mean, and also the spread. The spread is basically how away or how far away is the whole distribution from the mean. Is it having outliers, is it going too much out of control? Those kind of issues can be recorded in these control charts. So this is mostly in terms of piece to piece variability, okay, in the production process, and for this reason the control charts for variables are always developed and analyzed in pairs, okay. The first important variable control chart is the X chart, and this X chart is widely used for controlling the central tendency of a process, and these charts are based on either the sample range which is the R chart or the sample standard deviation which is the S chart. So basically you are classifying the variable control chart X chart into either a R chart, okay, which is the range based. So obviously as the name range suggests, it's the range of deviation from the mean that we are talking about, and standard deviation of course as you know is conventionally plotted as the mean square deviation, okay, from the mean sample, so or from the mean of the particular distribution. So that is the sigma that we are talking about. So obviously there is going to be an R chart and a sigma chart in the way that you represent all the X charts. So the range chart is relatively efficient and smaller subgroup sample sizes are involved in plotting the range chart. I am going to actually show you how to plot a range chart in a real problem, okay. So typically the subsample or the subgroup size or the subgroup sample size is below 8 when you talk about illustrating that on a range chart, but if it goes beyond 8 then obviously the sigma chart or the standard deviation chart has to be based upon or has to be called for. So the sigma chart is also better known as the S chart. S stands for standard deviation and they are typically with larger sample sizes. So I think I had made clear earlier that the way to plot these control charts is to sort of first of all record the mean value. So this is really the mean value, we can call this the control line, and then there is an upper control limit and the lower control limit based on how far away from the mean you are basing this particular two lines or two specification limits. It can be CL plus K R or plus K sigma, and similarly CL minus KR or minus K sigma that you are comparing here for creating the UCL and the LCL values. And typically the samples are plotted as points within this particular domain, and these are sort of recordings. You can see that how these controls or control lines with joining these different multiple observations can be obtained, and there are many interpretations which you can have from this particular control data. For example, you can see that there is a tendency of the quantity or the quality to shift, and this is recorded over a number of days. So you have probably some 10 days over which you are doing the recording, so day 1, day 2, 3, 4, 5, 6, 7, 8, 9, 10, maybe some more, about 15, 16 days. So you can see that below the or beyond the 7th day there has been a significant deviation in the way that the control variable is being plotted here, and so you can actually ascertain that something happened during the 7th day and beyond which caused this process to become more like an outlier from the mean tendency of the process. So very quickly you can actually see what are the aspects related to the process and do some countermeasures so that it can come back to control, like you saw that the process came back to control in this particular region. So that is how the variable control chart is plotted. Let us look at the attribute control chart. So as I already told you that there are many quality characteristics which cannot be measured on a continuous scale. For example, let us say looking into the polish aspect, that how bright is the or how good is the polish related to a car body, or maybe if you talk about the overall aesthetics of a interior of the car system, that is again something which cannot be measured. It is only the beholder who actually appreciates the beauty of the process, okay, in this particular manner. So you actually develop a rating scale onto the experiences of different people. Obviously the people are the customers who are going to use the product later on, and so their reference or their view is very, very important, and try to formulate that scale as acceptable 100% or 80% or acceptable 60%, and that way you create a scale, or even completely unacceptable for such attributes, and these are known as the attribute control charts, which do not have any hardcore measurements. It is only the intuition of a person that is being utilized here. So this happens when the quality of an item is judged either as conforming or non-conforming to a specification, okay. So you can have, let us say, as I told you, different examples in the car. Many other examples exist, like items having crack, missing components, appearance defects, visual imperfections may be rendered as rejects, defective, non-conforming items. So basically these are some things which there is no measurable basis of recording, and so that chart is known as a P chart. The P chart is basically for proportion of units which are non-conforming typically. So when we talk about a fraction reject, that is what really this term P means, that out of 100 samples, if we have rejected 30 samples, our P value is 30% in that particular lot. Simultaneously there are many other recordings of this kind of chart. There is the NP chart, where you talk about not only the units which are non-conforming, but the number of units which are non-conforming for samples of constant sizes. You have the C chart for the number of non-conformities or defects from samples of constant sizes. I am going to record and plot all these different charts as we go along. Then there is the U chart for the number of non-conformities per unit for samples not necessarily of constant sizes, and there are many interpretations which are there, and there are many situations where these are very important to take a qualitative decision statistically on the overall production process, to do something governing which can change really the process quality. So that is the attribute control chart. Let us talk a little bit about the benefits which are associated with the control charts. They provide a very, very large number of benefits. The compound effect of all these benefits is really an overall improvement in the quality, as you can see, related particularly to the process quality. And some of the distinct benefits are that the control charts are effective means of monitoring statistical control on a process, help to predict the performance of a process when the process is in the state of statistical control, and they provide a common language about the processes between maybe one or two different shifts which are being operating. For example, in a particular assembly line there may be a shift towards the morning, there may be a shift towards the evening, and there is really no interface between the supervisors of both the shifts unless they overstay, etc., which is again a financial burden to the company. So the control chart is really a way to share their experiences. So whatever has been processed or plotted as a quality parametric in the first shift can be just plotted in the diagram, and the supervisor from the second shift can just come and see the diagram to interpret that these are the areas where really there has been a deviation and where we need to focus in this particular shift so that the quality can be coming back to normalcy. So it is a sort of a unseen, it is a sort of a undefined kind of a language between 2 or 3 different shifts when they are running. It can be related to shifts of production or maintenance, or between again suppliers and producers, many different aspects. So without physically talking to each other, there is a way to sort of share their experiences using the control chart. Obviously control charts help direct corrective measures in a logical manner by identifying the occurrence of assignable causes. You can pinpoint again using the other tools of QC that I have illustrated earlier, that if a certain defect is coming, why it is coming. So if you have a recording of a certain particular defect going out of control, you can easily focus on that particular defect and then do the man material machine method analysis to see what are the different causes and try to eliminate those root causes, or even you can do FMEA as a matter of fact and try to see what are the most priority defects in the particular system. So some of the assignable causes may require special resources and involvement of management. So this helps in avoiding confusion, frustration, and high cost of possible misdirected efforts to solve a problem, and zeroes you down to the actual ground reality as to what is the exact cause of a certain problem coming in. So that is the overall benefit that the control charts would have. Let us now look into a little bit of these X bar charts and the S charts that I was talking about. So notations are of average and standard deviation for a sample of data. So let us first learn how to calculate these x bar and s, and then we will see what are the percentage observations typically which will lie between a certain range around the mean x bar in terms of number of times the s can be executed. So we think x dash as a typical value of x in a sample, or as a point around which the number tends to clutter. The standard deviation s is typically a deviation of the observation x from the average x bar, and it is a description, it is a deviation descriptive of variation within the sample. So from a well organized frequency distribution, as we have already seen above, we can say the following. So the between x bar minus x and x bar plus x, there will be about 65 to 70% observations. Between the mean plus minus 2 sigma limits or 2s limits will lie about 95 to 96% observations, and then between mean plus minus 3 sigma limits there will lie at least about 99% of the observations. This is typically how a normal distribution is programmed, and all the processes, as I think I have illustrated many times earlier, follow typically a normal distribution, okay, whether they are production processes, etc. And there are other distributions also which can be force fitted on this normal distribution, related really to the subgroup size, the sample size, so on and so forth. So we will talk about all that detail in the following modules. As of now, I think I will close this particular module in the interest of time, and in the next module we will discuss exactly how to calculate the x bar and s from distributions. Thank you.